All right, welcome everybody. This is your lesson on one of the options within the wave topic of the IB course. This is 4.2 traveling waves. We're going to basically do a bunch of theory in this flipped video, and which you're going to apply in a series of different stations when you come to your next lesson. Each objective that you can see currently is would relate to one of the stations that you're going to be completing. So I'd like you to take a minute to pause and just quickly read through those objectives yourself. You can do that now. Okay, welcome back. So before we carry on, I just want to do some quick recap from what we did previously. Some terminology specifically, like the time period. Remember, that is the time taken for one complete oscillation. We also did the frequency, which is the number of oscillations per second measured in hertz. We also covered the concept of wavelengths, from a measurement from crest to crest, or the distance for one complete cycle. We also mentioned wave speed, the speed at which the wave fronts would pass a stationary observer. And we also showed that frequency is period and frequency are reciprocals of each other. Okay, so your first objective was to describe the difference between what we call transverse and longitudinal waves. Now, first thing we need to remember is that all waves, traveling waves, take energy from one place to another, so they transfer energy. And there's two ways we can create a disturbance to transfer that energy, and that is to maybe beat a drum or to, beating a drum would be a good example. So for a transverse wave, the oscillations that create that disturbance are going to be perpendicular to the direction of energy transfer. Now, for an exam question, saying the words "the oscillations are perpendicular to the direction of energy transfer" will earn you the 2 marks for that sort of definition. If you have a look down here, you'll see that the oscillations, every single particle in the wave is actually also oscillating with the same frequency and time period as each other, but the overall net movement of energy is from left to right. Okay, so key things here, you'll see that the oscillations are perpendicular to the direction of energy transfer. Examples of these are water ripples, lights, ropes on a slinky. Should have said some of these when I went blank earlier, but I didn't, sorry. And they're also found as one of the two waves that are in earthquakes. Transverse waves are different to longitudinal waves in the nature of the disturbance of the waves. These waves, the oscillations that cause the disturbance, are parallel to the direction of energy transfer. So you'll see here the red disturbance is causing these particles within the tube to oscillate backwards and forwards with the same frequency that the disturbance is moving, but the overall overall movement of energy again is from left to right. You'll see areas within a longitudinal wave where you've got these areas of compressions and then areas of where it's spread out, which is a rarefaction. And the wavelength would be from the middle of one compression to the middle of the next compression. Note that longitudinal waves need a medium in order to move. There needs to be a particle that can be disturbed and oscillate, such as my vocal cords that are disturbing the air between you, well, you're not actually in the classroom now, but if we're in the classroom, between my vocal cords and your eardrums, which would then also oscillate with that same frequency, and that's how we detect what you're actually hearing. Examples of longitudinal waves would be sound waves, waves on a slinky. You can see the rarefactions and compressions there, and also you find longitudinal waves in earthquakes as well. So the key things to remember about when you need to describe the difference between transverse and longitudinal waves is the nature of the disturbance and if it is either perpendicular or parallel to the direction of energy transfer. Right. The two ways in which we can represent either longitudinal or transverse waves is through displacement distance graphs or displacement time graphs. And your learning objective for this is that you actually have to interpret information from either of these graphs. And in fact, one of the activities in the station you'll be doing is an exam question that asks you to do exactly that. So the two ways we do that is, firstly, we'll have a look at the displacement time graph. So you'll note on the axes we have displacement on the y-axis and time on the x-axis. And this looks at the movement of one point of the wave over a period of time. So to make this a little bit more explicit, I'm going to quickly just get out of there and go to here. Over here. And we've got a PhET simulation with a pendulum on it. When I push play here, we're going to be looking at how it is displaced over a period of time. We could measure the time period for one oscillation with our stopwatch over here, but it's continuous over a period of time. Alright, going back to our PowerPoint here, if we look at some more of the features of the graph, you will see that the distance from crest to crest here, or for one complete oscillation on a displacement time graph, actually gives us our time period, right? Because it's measured in time, it's a unit of time measured in seconds. Note that this could either be a transverse or a longitudinal wave. Students sometimes make this mistake of just looking at a wave like this and thinking, well, that must be a transverse wave. But this is a representation of this, how the movement displaces through time, so that could be applied to either a transverse wave or a longitudinal wave. Right, a displacement distance graph is different in the terms that it actually freezes time. You are looking at how far has it moved in a snapshot of time. To make that a little bit more clear, let's go back to our simulation here from PhET. If I push play, so we'd have to then pause it and now see, all right, what is the distance that it's moved from in this moment? What is the distance moved now after I freeze time? Freeze time again. What is the distance it's been displaced? What is the distance it's been displaced? You have to stop the time in order to analyze how far it has been displaced from equilibrium position, which is that middle line over here. Right, so what are some key features from this graph? Well, because we're doing a snapshot of how far it's moved from its equilibrium position, this gives us a crest from crest, or from one complete oscillation here would give us the actual wavelength, because it's measured again in a unit of measurement of centimeters. And it's also important to note that these could also be transverse or longitudinal waves. So please, like I said, when you do your exam question, when you come to class, make sure you're reading the axes so that you know what information to obtain from each graph in order to answer the questions that the exam question will be asking you. Okay, right. Another thing that you might be asked to do in the exam is to actually derive the wave speed equation. Now, this is one of the easier equations to derive, because we actually already know the equation to start from. But first of all, if we look at two variables that we're going to use to start our derivation, it's the time period, so we know what that is for one complete oscillation, and we also know the wavelength. So in this time, the wave would have moved one wavelength. All right. So we go back to the trusty old speed equals distance over time. The distance that we are referring to in this case is the wavelength. So we'd put that as our distance, and the time we're referring to in this case would be our time period. And that would look like that. So velocity, or our speed, would equal wavelength over the time period. But as we showed last lesson, and time period is equal to 1 over f, that velocity then equals f lambda. And that is the wave speed equation. So velocity in meters per second, frequency in hertz, and lambda would be in meters because it is a distance. All right. So this would be something that you'll also be practicing doing and applying when you come to the stations in your next lesson. Right. Moving on, determine the speed of sound experimentally. There are two things that I'm actually not going to be doing this right. I'm speaking to this right now, but this will be a lab that you will have to do. This is one of the 7 compulsory labs required by the IB. So we will be collecting this in as an official lab report, and you will do this experiment in your lesson as part of one of the stations. But please note, this is one of the 7 questions that comes up in paper 3 in your final exams. All right. Just to ease you in, there's a real interesting video here that you will watch as well, just to help you see that see something cool that these guys do with the speed of sound. Right, and then finally, one of the last things you need to do in this topic is to list the order of magnitude of electromagnetic waves. Now, electromagnetic waves, if you look over here, you'll see are transverse waves. They don't need a medium in which to travel. Good thing for us, because that way, energy can get from the sun to Earth, and actually we can be alive because of that. But electromagnetic waves are unique in the fact that they oscillate between 2 fields. They oscillate between an electric field and a magnetic field, as shown down here, and they can propagate through a vacuum. All right. So, types of electromagnetic waves. This will be something that you would have done before in previous science classes. I'm going to go this way quickly first, but essentially the only difference between the different types of electromagnetic waves is their wavelength or their frequency. So long wavelengths have low frequencies and short wavelengths have high frequencies. And the only difference is exactly that, the wavelengths and frequency. So radio waves have a long wavelength and low frequency, and then as we shorten the wavelength to microwaves, infrared waves, so what we feel is heat, which is next to the red on the visible spectrum. So this is the only small part of the electromagnetic spectrum that we can see, that our eyes have evolved to do so. Beyond that is ultraviolet, and then we have X-rays and the high energy gamma rays, and those would be our the electromagnetic spectrum. What you need to, sorry, I have skipped a slide. I should have probably put that. I just want to quickly point out here, which we'll cover again as well. Any electromagnetic waves travel at the speed of light, and the speed of light is denoted by the letter c, which is 3 times 10 to the power 8 meters per second. So if you see the wave speed equation written in this format, it's due to the fact that we are talking now about electromagnetic waves, and you know that speed. So they'll often forget to deliberately not give that to you in an exam, so that you need to remember what that speed is. All right. The requirement from the IB, if you look at the lesson objective, is to list the order of magnitude of electromagnetic waves. And this is the one thing that I hate to say, because I do not think learning should be about memorizing, but you unfortunately are going to have to memorize the orders of magnitude of these waves. Okay. So that brings us to the end of that. Like I said, you might want to go through those slides again and prepare, because you'll be applying the knowledge to do a series of activities, which I can probably quickly show you here. 1 second. My drive. I'm looking. There we go. Okay. Here we go. The stations. So you'll see here, it's the same objectives, but you'll have a station 1 where you're making a video on transverse and longitudinal waves using the keywords. You will then also be sketching displacement time graphs and displacement distance graphs, and then completing a exam question. You'll then watch this video and then complete the measuring speed of sound investigation. You'll then derive the wave speed equation and then apply it to this problem, and then you will fill in this table of the electromagnetic spectrum. Right, so thanks for listening and watching, and I hope you've done this, because if you haven't, you'll be pretty lost next lesson. Thank you.